we're going to talk about the energy stored in a capacitor. In fact, that's what capacitors are really for. When we use them in a dynamic circuit, we can use a capacitor to store up electrical energy, and then we can use that energy to do something else later on in a complicated circuit. We're going to review the definition of electrical potential and capacitance. And then we're going to talk about the work done to separate charge. And that's really where the energy stored in a capacitor comes from. If you're going to separate positive and negative charge, that takes work. And the work it took to do that is the energy stored in the capacitor. Then we're going to talk about this thing called energy density. When you create an electric field, you are essentially storing energy in the space. So how much energy do you have per cubic meter of space? And that's what we mean by energy density, the energy per unit volume of the space that's between, like the plates of a capacitor. Okay, well, let's define let's talk about potential again. Now, we define potential to be the work we do against some electric field. Like a change in potential was negative E dot ds, where the electric field is there applying a force to some charge that's in space. We move that charge through space. If we move against the field, if we move our positive test charge against the electric field, we're actually gaining electric potential. Here's what I mean. Like here's some electric field. It doesn't have to be a uniform field. So here's my E field. And here's my positive test charge. And I'm going to move it from point A to point B. And the nice thing is it doesn't matter what path I take from A to B, the change of potential is going to be the same. And but if I take a look at a little ds right here, here's my little, let's say my positive test charge is here and then it's over here, so here's my little ds, my little displacement vector. Notice that the displacement and the electric field are in opposite directions. And remember, this is a dot product, so this would be the magnitude of E at that position times the magnitude of ds times the cosine of the angle between them. Well, what is the angle between them if they're, in opposite directions? It's 180 degrees. The cosine of 180 degrees is -1. It cancels out that negative. So you can see that as I move from here to here, I'm gaining potential. Now, what are the units here? This is newtons per coulomb times meters. Newtons per coulomb is the electric field. Meters is my displacement. That's a joule per coulomb. And of course, a joule per coulomb is a volt. So we're gaining voltage as we move against that electric field. But what if I want to know how much actual energy did I store? Not potential, but potential energy. And this is the confusing part of this whole vocabulary we use. When I say electric potential, I'm talking about joules per coulomb. When I talk about electrical potential energy, I tack on that word energy onto that phrase, it means joules. So to do that, we'll just say, well, delta U is just equal to whatever charge I have on my test charge right here times the voltage difference between A and B. And that'll be the energy that is stored up. And that's really what I want to know. That's the question I want to answer, is how much energy in joules is stored up in a capacitor that's charged up. Okay, well, remember what we do in a capacitor is basically I have a blob of metal over here and a blob of metal over here. Okay, this is not any kind of practical capacitor. This is the capacitor in the most general sense. And what I'm going to do is I'm going to deposit positive charge over here, right? And an equal amount of negative charge over here. And that creates an electric field. Just like in the video. Okay, it comes out of the positive and in here. Okay, and so what I have is this quality of these two guys, which I'm going to call capacitance. And it's the charge, and I can call, let's say this is fully charged. It's the total charge I've got on this capacitor divided by the voltage difference between these plates. Now, what is the voltage difference? Well, let's say I take a little tiny positive test charge and I move it against this field to go from this surface to this surface. That's the voltage difference between those two plates. Okay, so and this is my definition of capacitance. So here's the deal. When I separated this charge, I had to do work to do that. I mean, somebody from the outside had to come in and say, look, I'm going to take positive charge off of this plate and I'm going to deposit it over here. Well, is the energy, therefore, the energies of this capacitance, here's a naive way of looking at it. So this is actually going to be wrong, what I'm about to write down. You say, oh, okay, well, delta U equals Q times delta V. Well, let's solve for, we could solve for delta V. Let's just solve for delta V from this equation. Oh, okay, well, delta V is equal to Q over C. Now, there is a difference between this charge and this charge a little bit. We're going to get to that in just a second, but for now, don't worry about it. So what I can do is do a substitution. I can go Q times the total charge over the capacitance. And you say, oh, okay, it's Q squared over C, or something like that. And you'd be wrong. Because the work done, well, let's take a look at this from the beginning. Okay? So here's my positive, or one of my plates, or one of my metal things, and here's the other one. And they're going to start off being electrically neutral. There's no charge separation when I begin, right? And so what I'm going to have to do is take some positive charge from here and deposit it over here, leaving a negative charge behind. Okay? Now this looks like a field line, so let me erase that and just say, okay, I'm going to pick up some positive charge here, and I'm going to move it over here. But do you see that it took almost no work to do that? I'm not working against an electric field. There is no electric field yet because there's no charge separation yet. Well, now there is a little bit of charge separation. But the field is incredibly weak, right? From this little bit of charge. Now, of course, this charge will be smeared all over here, and this will be smeared all over here. But there's very, very little charge separation, which means the electric field is weak. Now, the next little bit of charge that I'm going to try to move, I'm going to take a little bit more positive charge from this guy and move it over here. Okay, leaving another. Now, that took a little bit more work, didn't it? It took a little bit more work because there was now an electric field there. Well, now the field's a little bit stronger. So now to take another positive test charge away from here and deposit it over here, now I've got to do more work per unit charge to go from here over to here. In other words, the voltage is dependent on the charge. And so you can't just you can't, and the voltage is varying with the charge. So what we're going to do is this. I want to know how much energy difference is there between here and here. In other words, how much work do I need to do to get from here to here? Well, let's say there's at any given instant there's delta V, and I'm going to move a charge from here to here. So a little tiny bit of work that it takes to do that is going to be equal to, I'm going to take a little tiny bit of charge and multiply that charge by the voltage at that instant. So this, okay, so the work it takes to move a charge from here to here, which will be the energy stored after I add up all the work, is equal to a little tiny bit of charge moved times the voltage. But this voltage depends on how much charge is on how much charge has been separated. And the more I move it, the more charge there is. So here's the difference between capital Q and Q. And this is right out of the book, so you can read the book. I'm going to use Q is the total, am I still on the screen? The total charge. We use capital Q to, like we use capital R, like for the radius. Like that is the radius of our thing. Capital Q is the total charge I have on my capacitor when I'm done. The maximum charge I'm going to put on it. Little q is going to be the charge that it's time dependent. It's varying. It's the charge I've got at some instant as I'm doing the problem. Okay. So I want to add up all the work it takes to go from here over to here. Okay, so that's going to be, this is going to be the work. When I add up all the little bitty works, it's going to do that. And now I want to be able to integrate here. Let's just go delta V times dq, just so it's in the right order. All right. But what do we know about delta V? Well, delta V, in terms of the capacitance, is equal to Q over C. So let's substitute that in there. So the work it takes is equal to Q over C times dq. Now, what are we going to vary? How are we going to vary the charge? Well, how much charge was on the plate at the beginning? None. Zero charge. And how much charge am I going to end up with when I'm all done? What am I going to call that charge when I'm all done? Capital Q. So this Q is going to vary from 0 to capital Q. Total charge. Yes? Yeah, question.
Why is the little q, where it's Q over C, why is that little q and not big Q?
Well, because I think you get this right here, this one, this is kind of the total voltage at the end of the problem. Okay? When I'm done transferring over charge, this is kind of the total voltage is equal to the total charge over the capacitance of the system. All right? But this is the voltage at the given moment when I have this amount of charge on it. So I'm not done adding charge. I'm going to add some more charge on it. So in other words, what I'm trying to say is that the voltage between these plates varies as directly with how much charge I've separated. Well, now it's easy to integrate this one. No natural logs required. This is just going to be, well, the 1 over C comes out. Q times Q is Q squared over 2, varied between 0 and Q. So I'll substitute in Q for lowercase q, and then 0 just goes away. So the work done is equal to 1/2 Q squared over C. So you have this 1/2. Now, when we naively looked at it without using integration, like we did over here, we would just have Q times Q, Q squared over C. But no, it's 1/2 Q squared over C. That's what you have to do. So that's the work it took to separate all that charge. We get all that work back when we discharge the capacitor. So, in other words, the charged capacitor is storing energy for us. It's a form of potential energy. So we can say the potential energy, U, stored in a capacitor is equal to 1/2 Q squared over C. And that's the energy stored in a capacitor. Now, there's different ways of writing this, though, okay, because we have the expression for capacitance. The capacitance is equal to the charge over the voltage, V, voltage. So just substitute this in there, and you get U equals 1/2 Q squared over Q over delta V. And when you do that, you get 1/2, well, the Q cancels with the Q squared, the delta V comes to the top, Q delta V. Now this makes sense, doesn't it? Just dimensionally, coulombs times joules per coulomb is joules, but you have this 1/2 there. Or I can solve for Q and make a substitution. Q equals C times delta V. So I go 1/2 of C squared delta V squared over C. So the capacitance cancels, and I get 1/2 delta V squared over C, over the capacitance. So we have these different, these equations that we can use to calculate the energy, depending on what we're given. Yes? Yeah, I'm sorry, thank you. The C is right there, that's right. C delta V squared. Okay? Just testing. All right. I'm running out of time. I want to talk about the energy density. Now we can apply this to a parallel plate capacitor. Let's take a look at a parallel plate capacitor. So here's a wire leading up to it. There's a parallel plate. There's a parallel plate. And if I, thank you. And then if I put positive charge on here, there's Q. I've got an electric field in here. So I got negative charge on over here. All right. Now there's a volume of space in here. So what I want to do is get the energy stored in this capacitor divided by the volume of that space. And I get something kind of interesting. Okay, so what is the well, we have energy, the potential energy stored in a capacitor of 1/2, which one do we use? I'll use 1/2 C delta V squared. It turns out to be a little bit easier to do it with that one. Well, this is a parallel plate capacitor, which we earlier derived. The capacitance of that is epsilon naught times the area of the capacitor divided by D, the distance between the plates. And then delta V for this kind of capacitor is just the electric field, the strength of the electric field, E times D. So this is going to be E times D. That's the voltage difference across this plate, but we're going to square it. So this is 1/2 epsilon naught A over D, E squared, D squared. Now what I'm going to do is play around with this, just algebraically. 1/2 epsilon naught. I'm going to go A, oh wait, this cancels with that. So I'm going to go A times D times E squared. But what is A times D? A is the area of one of the plates, and D is the distance between the plates. So what do we get when we have A times D? That's the volume contained between the plates of the capacitor. So what I'm going to do is I'm going to define this little thing called lowercase, well, it's kind of a lowercase u, I think it's upsilon or something like that. It is equal to the potential energy stored in the capacitor divided by A times D, the volume, energy per unit volume, and that's equal to 1/2 epsilon naught times E squared. Now the bell's about to ring. I got 1 minute left. But here's why this is cool. I derived this easily using a parallel plate capacitor. Oh, it's a late day. Okay, I can slow down. Thanks. Thanks. I always... okay. It's a late day. I got 10 more minutes. Okay. So what this tells me is this, is that the energy density that is joules, which is basically in terms of units, it's joules per cubic meter in the metric system, right? Because there's an electric field, just because there is an electric field, there is energy contained in that space. And the energy contained in that space is going to be 1/2 epsilon naught. Okay, these are just constants of nature. 1/2 is a constant of nature, right? And epsilon naught is just a property of our universe times the electric field squared. And now I'll tell you, and we call this, this little thing right here. So this is an equation that you will see a little bit. This is not a huge deal for this class. Okay? And on the AP exam, in AP Physics, you may get one multiple choice question about it. It's not a big deal. It's a big deal later in physics, though. So I used to kind of gloss over this, but then I took some graduate level courses at Fresno State and upper division courses at Fresno State, and this became a much more important idea. But here, think about it. If I took a little, cube of empty space. Oops. If I took a little cube of empty space, just some little volume, there is electric field moving through it. I can say there is energy contained in that space. Yeah. Energy in empty space. Well, because there's an electric field in there. So this leads to some pretty amazing things when you get later on in physics. And there's a couple of questions, but it only depends on what the electric field is. Now, of course, this little equation doesn't, what if the field is varying with space, which a lot of electric fields do? Well, then you have to make your volume really, really tiny, and then if you want to know the total, you have to integrate or whatever. But if you have an electric field, there is energy associated with that electric field, energy per unit volume. So, okay, that is, I think we get everything. Please, always go back and think about, as we're studying E&M, it's very easy to forget what the basic ideas are as you're trying to use those basic ideas to develop new ideas. You really have to understand what potential is and what capacitance is. What does it mean in our little world of positive test charges and electric fields and so on? Remember, it takes, I think did I misspell separate here? Doggone it. There's a rat in separate, right? A rat. I learned that by watching 1 out of 12. All right. Energy density. There's energy in empty space if there's an electric field going through it. Pretty cool stuff. All right. That is all.